I'm going to describe and show how to use Excel Solver to carry out nonlinear regression, in particular where we want to determine an activation energy and a pre-exponential factor for a chemical reaction. And the rate data, temperature, and the corresponding rate constant, that temperature, that we'll use in this nonlinear regression. So let's look at the spreadsheet, a copy of the spreadsheet, so I can explain what the terms are. So here I'm showing this is just text that's showing the form of the equation where we're fitting the pre-exponential factor and the activation energy. In these two cells, we enter our guess values, and what I'm showing here is after we've run Solver. These are the cells that we adjust, and here are our final answers. If I have K0, I can calculate the pre-exponential factor because this is just equal to the K0 times E over R T0, where T0 is halfway between the highest and lowest temperature, namely 770 Kelvin. And so if we look at the spreadsheet values, the experimental values here, notice this is just the mean of the values, and we're doing this calculation because we want to calculate the R squared value, and we're going to use that. Here is the formula, namely this formula, where we've adjusted K and E to minimize the sum of the squares. And so the sum of the squares is the difference between our experimental value and our calculated value, and we square that. Here's the sum of the squares. That's what we minimized in Excel. Mention we calculate the mean value. So in this column, what we're calculating is our experimental value minus the mean value for K. And then we sum the squares, right? So this is the difference squared. And here's the sum of those values. And then R squared is just equal to 1 minus SS over SS mean. The other terms, degrees of freedom, well, this is the number of data points, in this case 6, minus the number of parameters, so that's 4. And then the standard error, well, this is the square root of sum of the squares divided by the degrees of freedom. Now, the run number, we look at this is the difference between the experimental and the calculated values. These are also called residuals. And we look at how many separate sets of numbers of the same sign we have. So this is 1, they're both positive. This is 2, they're negative. This is 3, positive. 4, negative. So the run number is 4. The expected run number, well, this is the number of data points over 2 plus 1, which happens to be, in our case, also 4. Well, we also can look at, I'll show you a copy of the spreadsheet that displays the formulas. So the calculated value using the formula that's up here, as I mentioned, you see how we calculate the difference between experimental and calculated, square that, and then the sums of the squares, and our formulas that we mentioned for the different values. So this just shows the exact same information, but shows the formulas as opposed to numerical values. Let's look at the actual spreadsheet. Well, here's the spreadsheet that I just showed you. I've put in the guess values now in yellow. And what I'm going to do, the yellow here for the sum of the squares, sum of this column, where the calculated value, the formula is shown up above here. And it corresponds to this formula here. So run Solver by going to Data, Solver, and now I'm minimizing the cell which I've named SS. Minimize. I want positive values, and I'm changing K0 and E. I select Solver. Gives me an answer, and here are the values for K0 and activation energy. I then can calculate the pre-exponential factor, 3.53 times 10 to the 12th, because remember pre-exponential factors for this formula here. And I've written the activation energy in kilojoules per mole since that's the more common way. What I'm also showing in this spreadsheet, I calculate the inverse temperature and the log of the values, and I also calculate the difference between the experimental and the calculated value. So here I plotted the log of the rate constant. The green squares are the data points, and then the blue line and the blue circles are the calculated values, where the blue line is a trend line, so it's a straight line fit through the calculated values. You can also look at the residuals, namely the difference between experimental and calculated value, and see there's no pattern, there's no trend. It appears to be a random distribution of the errors. So we can see with the spreadsheet, we can quickly calculate the best fit using nonlinear regression. We can also calculate the confidence intervals, and I'll explain that in a separate screencast.